Modeling censored data with Tobit. In this talk, we'll define censored data, discuss why modeling it is important, and introduce the Tobit model for censored data. Censored data is data where the values of some measurements are only partially known. For example, here's a table recording subject lifespan in months as a function of several input variables. Note that for some of the subjects, it's only recorded that they lived 24 months or longer, but not exactly how long. This is censored data. This is a common situation in clinical trials and often happens because some outcome values are beyond the range that can be measured in the experiment. For example, this experiment only lasted 24 months, so the experimenters can't observe the actual lifespan of any subject who survives past the end of the trial. The goal in modeling censored data is to correctly estimate the relationship between inputs and outcome, and to extrapolate that relationship beyond what can be measured. Let's use an even simpler example to motivate the rest of the discussion. Suppose that you run a pie shop and can only bake a maximum of 50 pies a day. You know that spending more on marketing directly increases pie sales, and you want to know the relationship between the two so that you can answer questions like, if I want to sell out all my pies every day, what is my optimal marketing spend? Or, how much should I spend on marketing if I increase production capacity? Here's some data that you've collected on daily pie sales as a function of marketing spend. The x-axis shows the marketing spend, and the y-axis shows pie sales. In statistical parlance, the daily pie sales are the observed outcomes. And the expected number of pies that you could sell for a given marketing spend if you had infinite baking capacity is an unobserved value that we'll call demand. Actual pie sales are either noisy or incomplete observations of the demand. And what you really want to model is how does marketing spend affect demand independent of the current production capacity. Standard machine learning approaches have some shortcomings when it comes to censored data. First, standard methods assume noisy but complete observations of the outcome. And while a standard model can potentially predict the expected observations in non-censored regions of the data, the model won't necessarily estimate desired unobserved outcomes very well. And sometimes the model won't predict well even in the non-censored regions. In our example, if we try to fit a linear model to the censored pie sales data, we see that the model gets the relationship between marketing spend and demand wrong, even in the observable region. So we don't feel confident using this model for decision making. Note that we can see here that the fitted model is obviously wrong in this single variable situation, but the discrepancy between model and observations will be less obvious with high-dimensional multivariate data. If we cap the model predictions to 50 pies, we can measure the root mean squared error, or RMSE, of the model, which is about 7.7 on the evaluation set. Nonlinear models like random forest might predict better in the observable region, but they still can't extrapolate pie demand beyond what's been currently observed. In particular, if we ask this model to predict demand rather than sales for marketing spends of $60, $75, or $90, the model will predict 50 pies every time, even though we know that higher marketing spend should increase awareness and hence demand for the pies. If your data is censored and you believe that the data process is roughly linear, you can try the Tobit model. I won't explain the Tobit model in this talk, but simply show you the results. You can find functions for fitting a Tobit model in either R or Python. Here are the resulting capped Tobit model predictions for our pie shop data. It's a pretty good fit to the data and has an RMSE of about 4.6. This is much better than the previous model, which you remember had an error of about 7.7. For this synthetic data set, you can also compare the uncapped model predictions to the true unobserved demand, which is plotted here in purple. While the predictions aren't perfect, you can see that this model would be good enough to address the business questions we considered at the beginning of this discussion. For example, how does increasing pie baking capacity affect marketing spend? As I mentioned, functions for fitting a Tobit model exist in both R and Python. For this example, we implemented the Tobit relationships directly into the probabilistic modeling package Stan. We then let Stan infer the unobserved demand that was most compatible with the observed sales. The advantage of using Stan rather than a pre-existing package is that we can vary the modeling assumptions away from standard Tobit assumptions. For example, we can try assuming that the unobserved demand is nonlinear in price, if we know how to express this nonlinearity. The disadvantage, of course, is that using Stan requires familiarity with Stan, as well as experience in probabilistic reasoning and in expressing different assumed processes in probabilistic terms. If you are interested in exploring whether probabilistic methods can help with your application, please reach out to us at WinVector LLC for training or consulting. Thank you very much.